and industrial applications. In the last 1 decade, the area of nanotechnology has been emerging as one of the fastest growing domain with new promising technologies development for the next generation and beyond. Also, under the banner of IEEE, participants receive numerous opportunities to publish and collaborate their research network with professionals. Optica, which is formerly known as OSA, is a platform where we celebrate the society and the science of optics and photonics over the past century and beyond. Optics and photonics are the specialized field of physics and engineering that enables high-tech manufacturing, high-power laser, nuclear threat identification, solar power, scalable quantum computers, and other technologies, which are critical for health and safety for individuals worldwide. Optica stands to be the world's most accomplished leaders in science, engineering, and business with more than 22,000 members and connect you with an unparalleled global network of leading professionals. Now, I would like to give a brief introduction of our guest speaker. Dr. Nithin M done his B.Tech in the Electronics and Communication Engineering from Mohandas College of Engineering and Technology and M.Tech in VLSI Design, Ph.D. in Radio Frequency IC Design, and both from the Vellore Institute of Technology, Vellore. He specialized in the courses like Analog Microelectronic Circuit, Analog IC Design, Mixed Signal IC Design, and Radio Frequency IC Design for undergraduate and postgraduate students. He has teaching experience of more than 10 years. His research interests are analog RF domain of VLSI and working on design of RF circuit for transceivers. He has published more than 20 papers in international journals and peer-reviewed conference. Currently, he is pursuing a specialized course in the IC design at University of California. He also has a YouTube channel named Nithin M with 100+ videos on the courses taught so far for the benefit of a wider student community. Now, I welcome our respected speaker, Dr. Nithin, on the behalf of IEEE NTC chapter and Optica student chapter of PDPM IIITDM Jabalpur. We really appreciate that you accepted our invitation on such a short notice. Thank you so much, sir, for accepting once again. And now over to you, sir.
Thank you so much, Ankit, for that nice introduction. I hope I'm audible, Ankit.
Yes, sir, you are audible, sir.
Yeah, so I'll share my screen.
Yes, sir, it is visible, sir.
Okay, yeah.
Sir, can you make it full screen, sir?
Yeah, sure. Is it perfect now?
Yes, sir.
All right. So should I keep my video on, or I don't know about the bandwidth issues while presentation? You want me to switch on my video, or I can?
Sir, it's up to you, sir. You can switch it on, sir. There is no issue of the bandwidth from our end, sir.
All right. Thank you. Yeah.
Thank you, sir.
Yeah. Good evening to one who are listening here, who are present here online. And first of all, I would like to thank IEEE NTC chapter, especially Dr. Navjit Vaga, because he's my very close friend, and through him only this invitation has come. Also, I thank Ankit for organizing and coordinating this event. So the topic of presentation is fundamentals of analog design, present day challenges and future opportunities. As I'm working as an assistant professor in RV College of Engineering, Bangalore, and I'm teaching VLSI related courses for more than 10 years. So as an intro, I can see around 69 participants here. While this was advertising, I also took a pre-webinar survey kind of thing, which with few questions. I don't know how many of you have seen that. I got few responses through that questionnaire. So why I have taken that like a survey is basically to know the audience, and I can tune to your requirements. So from the questionnaire and from the responses from some of you, what I understood is more we're looking for the fundamentals. Even the lecture title was also on fundamentals of analog design. So I'll be talking about fundamentals. And before talking about fundamentals, I also see that at least majority attending today belongs to first year. All right. So majority belongs to first year, and for that reason, I'll be I'll be focusing on like how electrical engineering, like starting from the branch, starting from engineering, how we can connect science and engineering, and then how we can move forward, and we can talk about electronics engineering, and finally to VLSI design, and then from there how analog design will make some impact today. Yeah, please feel free to post your questions in the chat. And I can see that Chirag has a request. Chirag, I'm very sorry. I'm not fluent in Hindi. I can understand Hindi. So I would like to continue my presentation in English. I'm very sorry for that. All right. Yeah, so I have divided this lecture into 4 parts. The first, second, and third part, I do have a presentation. And the third part is more like it is not a presentation. If you're interested, I'll be actually helping you out to understand some of the fundamentals through a regular lecture method. All right. So the first 15 minutes, what we will be focusing will be on the discipline of electrical engineering, then the electronics and communication engineering and the domains under that, and why analog design. So why today in this digital world, why we need to talk about analog design, what is analog design, and finally the relevance of analog design. So this will be the first part of the presentation. If you feel that the presentation is going in a faster pace, please do intimate in the chat box. I'll also request you to keep yourself mute the other time, rest of the time. Yeah, so just to start with, see, I'll be keep on asking some of the other questions. Those who are free, those who want to respond, please do respond in the chat box. So I would like to start with this question. What is the basic difference between engineering and science? Or when you hear about engineering or when you hear about science, so do you find any difference between these two? If you have any responses, please, you can put in the chat box. For every question, I may wait for 5 or 10 seconds and I'll proceed because I don't want to take much of your time, because on a Saturday afternoon, in the evening, you guys are free and you have come to listen. So I'll not be taking much of your time. All right. So see, I'm not just giving a very the perfect or a very demarcating statements here, but rather, yes. Thank you, Kapil, for that. Engineering is application of science. Yes, true. Ritika Mishra, thank you so much for the response. Right, that is absolutely right. So when you hear about science, science is something which describes and understands about the natural world, and often we call the people who do that or who describe and understand natural world, we often call them as scientists. In a similar way, engineering, as some of you responded, it is actually the use of science or how you will apply science. Or to be very precise, we can also see that engineering is actually the solutions to the problems around us, and people who does that, we call them as engineers, right? So I hope those who are listening to me all are coming to the category of engineers. So we seek. Yes, Chirag, that is true. It is a practical state of science. All right, something in practice. Yes, I agree to that. So to start with a very simple example, so what you can see is a water tank which is kept at a height, and definitely you would have studied about the potential energy, right? So when you keep when there is a object of mass which is kept at a height, definitely it will hold some potential energy, and that is science what we learn. Now, when you convert that knowledge into to solve a practical issue, in the sense, say for example, we want to provide water to an area where there is scarcity of water, and then by placing a tank at a very height, on a high level, by knowing that this potential energy will be converted into a kinetic energy, and this can actually supply water to the nearby places. This is actually the solution to the problem. This is what engineers tend to do. Right. So this could be an example which everyone can relate. And now, if you come to our present day, where all of us are connected each other using our mobile phones, right? I hope most of you who are listening to me will also be seeing me through your mobile phones, right? So now, when you look at this mobile phone, that is also actually mobile phone is also the invention or the science behind is like we can communicate. Wireless communication is possible, and as a result of that, these many gadgets has come up, and mobile phone is one such device which made our life very, very easy. at this time, right? Now, so I can conclude here that engineering is actually the use of scientific knowledge, to create a technology. All right. So I hope you agree to that. Now, moving on. So I just want to review about the industrial revolutions which happened so far. So at least some of you would have heard about these revolutions. Like we number it as Industry 1.0, which was about steam. Industry 2.0 was about electricity. Industry 3.0 was about computing, and Industry 4.0 is about connectedness. That you'll be often hearing about this these days. So when you look at this as an electrical or as an electronic engineer, we will be more focused, or we can say that the growth in electronic industry, or the growth in semiconductor industry, has rapidly evolved after Industry 3.0. And if you look at that, you will see that automated production, electronics and computer, semiconductor industry, those things has developed with the third industrial revolution. And today you can see that everywhere you're hearing about artificial intelligence, machine learning, big data, robotics, everything. So those things, all these things has come after this third revolution, where a lot of automation happened, a lot of electronic gadgets has come. And today we see that we are connected anytime, anywhere we are connected. And that is actually that is the result of this industrial revolution. Now, quickly coming to the electrical engineering branch, the parent branch, I'm sure that at least most of you will be knowing that the electrical engineering is actually the parent branch, right? And the electronics and communication engineering, what we hear today, has evolved from this parent branch. So if you look at this parent branch, it is having all these components inside, or all these subdomains inside. It talks about communication. It deals with embedded systems. It deals with instrumentation and control systems. It deals with photonics. It deals with signal processing. It deals with power systems and electronics. It deals with nanoelectronics. It also deals with integrated circuits and systems. All right, so these are the various domains in electrical engineering. But at least in most of the IITs, still they call the parent branch as electrical engineering or electrical and communication engineering. But most of the other affiliated institutions, we talk about electronics and communication engineering. So here the focus is, when at the moment we say that the branch is about electronics and communication engineering, we deal with at least four specific domains in little detail. One is VLSI design, where we talk about integrating lot many components on a single substrate. Then we talk about signal processing, where we talk about signal processing or image processing, or all those domains. Then we talk about communication, which helps us to understand about communications and the related networking part. And finally, embedded system, where we bring all these things together, and when we get it as a finished or a final product. All right. So talking a little more about VLSI, which is my area of specialization, where I was talking about one of the major domain of electronics and communication engineering is VLSI design. And if you look at the subdomains of VLSI design, you can see that there are various subdomains where we talk about devices, where we talk about circuits. There again, you can classify as analog and mixed signal designs, RF designs, digital designs. Then we talk about MEMS and NEMS. We talk about testing, testability. These are some of the subdomains what I have marked over here. But everything starts with device and device physics, right? So hope you have come across many devices, electronic devices. Especially I'm talking about active devices, starting from transistors, what we call it as bipolar junction transistors, or later we hear about field effect transistors like MOSFETs. And these days, I'm sure that you are hearing about the better versions of MOSFETs. When I say better versions, in different aspects, like FinFETs and other things. And even generally, before, when we talk about devices, we'll be hearing about devices which is made out of silicon. But these days, or at least more than a decade, we are actually also hearing about devices which made out of other semiconductors. We call it as compound semiconductors, right? So everything starts with the devices. And with the help of many different new devices, we are designing different circuits, and those circuits are actually helping us in as in various things, a number of things. So one simple example, if you take your mobile phone, today my entire presentation will be around mobile phone. I'll be talking circuits and will be linking that to your mobile phone, because that is something which you can easily connect. Right. So devices, circuits, and then there are a lot many other things. When I talk about circuits, I should talk about analog signals. I should talk about digital signal and the combination of these two. Right. Now, and then the question what I want to pose here is, or even I don't know how many of you will be thinking in this digital era, or when everything is digital, when we hear about everything as digital, what is this? What is the importance or what is the significance of analog? Or along with that, you might get all these questions also into your mind, that why analog in today's digital world, or why are we interested in analog design, or isn't analog design old and out of fashion, or will there be even jobs for analog designers? These might be some of the questions which comes to your mind. If you are a first year student, I don't think you will have all these questions, but at least if you are progressing in your engineering studies, you will be thinking, why I need to bother about, or why I need to learn about analog, right? So I hope this webinar this lecture will give you at least some idea or some answers to some of these questions. All right. So coming to the first question, what is analog? So can I get some response from the audience in the chat? What comes to your mind when you hear the term analog? Can I get some response from you guys in the chat? Continuous time signal. Thank you, Rajan for that. Signals, all right. Real signal, fine. Yeah, thank you for the response. Yeah, so before talking about, so when the moment I say analog, I can say that, or I can tell that everything we see, everything we hear, and everything we perceive in life directly from this world is analog, right? I hope you will agree with me for that. Just to add up, it could be a voice, it could be a music signal, or it could be a seismic activity, or what else, whatever we hear or whatever we see, whatever we perceive in this from this nature is analog, right? Now, when it comes to engineering, or when we talk as an engineer, we'll try to represent this information. So whatever information we are getting from the nature, we'll try to represent in the form of the electrical representation is nothing but we call it as a signal, right? So the moment you say analog signal, the information, whatever information we are getting, when we convert that into electrical form, we call it a signal. Now the question is, how do you convert that into electrical form? We do have sensors, different sensors to pick up these signals and to convert this into electrical form, right? Now, this is the one way you can actually represent a signal. So the moment you say signal, basically you will look at two characteristics. One is the frequency of the signal, and another one is amplitude of the signal. And what you can see on the screen now is a simple analog signal, where you can see that as some of you responded, it is a real signal. Yes, analog signals are real, and it is continuous also. When I say continuous, at every instant of time, there will be some value for that, right? That is what we mean by analog signal. Now, so it will have a specific amplitude, or it could be a varying amplitude signal, and it will have a specific frequency, or it will be having a range of frequency within. So so I hope you understand what is a signal. It is electrical representation of any information, and analog signal is having this nature of continuity, right? So to be very precise, we say that the signal which is continuous in time and continuous in amplitude are called as analog signal. And now the circuits which process these analog signals are called as analog circuits, right? So here the main focus, or what we will be focusing, is more on analog circuits. Now, before moving to analog circuits, now I just want to ask, now why we are actually talking about circuits, right? Why we need to talk about circuits? Because in every system, wherever, like whenever we deal with in today's world, whenever we deal, say for example, you're going to an auditorium and sitting here and listening a speech from someone, or if you even in your classrooms, or even now when you're listening to me through this online platform, everywhere you can actually see a system. And to be very precise, I can call it a signal processing system. Now, if you look at a typical signal processing system, if I represent that in the form of a block diagram, I can represent in this form, where you will have signals of which are continuous in time and continuous in amplitude, which we call it as analog signal. I hope you can see that here. on my screen. Now, those signals will be picked up by something called as sensors, because if I need to process this analog signal, I can actually pick up those signals. Now, the question comes, why I need to process analog signals? So the answer is the naturally occurring signals, what we get from the nature, in whatever form it is, whether it is the voice signal, whatever is coming from me, or whether it is a music or whatever it is, all are feeble, weak signals, which will be of the magnitude of either milli or microvolt range. So if I need to work with those signals, I need to process it. So the processing is basically done. The set of processes will be there, are there. So if I want to process that, I need to first pick up the signal, and for that we use sensors. Now, after picking up the signal, we know that we all are enjoying the benefits of digital, right? So if I ask you why do we go for digital? Can I get some response from the chat? Why do we go for digital? So can we call wave as signal? Yes, Anish, yes, definitely you can call a wave as a signal. If you, I don't know which wave you mentioned. If you see the movement of a water, yes, if you're continuously recording the movement of a water, yes, definitely it is a signal. Recording and representing it in electrical form, it is a signal. Yes, computer understand digital language. Yeah, that is true. Okay, now again, why this digital revolution happened? Yeah, probably you can see the slides over here, easily accessible from electromagnetic. Oh yeah, yes, of course, yes. All right, yeah. So when the moment we say digital, so as I was discussing, analog is something which you see in real, right? So analog electronics, or the electronics part, is basically it will link the real world to the sorry. Yeah. So you can see that the signals will be picked up by the sensors, and I need to process the signal. Now, why the processing is required? Because as I can see the responses in the chat, we want to process in digital because of the lot of advantages what digital give. So to number a few advantages, I can say that the very important thing is noise immunity. I can say, yeah, ease of accessibility. Storage is one another important thing, right? Prerit, yeah, regarding accuracy, yes, we need to talk about accuracy. But one thing we can say, the storage is very, very easy compared to analog storage, because storing analog signals, analog memories are there is difficulties associated with that. Say for a simple example, if capacitors, so for example, capacitor, if you store an analog signal, we know that it will leak, and the charges will actually leak from the signal, right? From the capacitor. So storage wise, I can say that analog signal, digital signals are more advantageous, right? So we need to convert this analog signal in digital for processing, easy processing, or for easy storage, right? So for that we need some blocks. You can see the blue boxes which is on the screen now. Those are called as interface electronics, which will help you in converting analog signal into digital signal. So I was telling about analog signal as continuous in time and amplitude. At the same time, we can say that digital signal is something which is discrete in time and discrete in amplitude, right? So the interface electronics, which sits between the real world and the digital world, or the real world and the simulated world, is called as data converters, which belongs as A to D converters and D to A converters, which helps in converting from analog to digital, and from then back from digital to analog. So why do I need to convert it back to analog? Because if I want to perceive it, again, it should be analog in nature, right? So in between, what you're seeing in the red is actually your digital processing. There, now I can say in 2021, if I'm talking about analog, you can see that digital has expanded like anything. Now the main challenge here is how I can support this expanded digital with the analog circuitry, because still the natural signals will be analog, and as long as human exists, we also will perceive only analog signals, right? So I need even though we say that the digital is expanding like anything, the challenge and the task will be more on the analog side, because we need to come up with circuits, or we need to come up with systems which will be compatible with this expanded or this most modern digital systems. All right. So to summarize the points, Well, yeah, I don't know, because at least my students have asked me, sir, why we are still talking about analog, because world is going digital. Yes, the answer is what we have discussed just now. Analog electronics links real world to digital world. Physical signals are analog and they are continuous in time and amplitude. Digital signals have higher noise immunity and the storage is very easy. But with that, we cannot say that we cannot leave it, or we can forget about all the analog circuits or the systems, right? Because we cannot do that. We need to interface, we need to condition, and we need to process analog signals in order to present that signal into a digital system where it can actually represent in a better digital form. All right. I hope my pace is okay. If not, please mention in the chat box. All right. So moving on, I just want to present you the chipset of iPhones. iPhone is, I think, this iPhone 7, what I have here. And if you look at the chipset of this iPhone 7, I don't know how many of you will understand this. If you are first year students, definitely you can read out these terms and you will see that there are a lot many things in your IC. Like if you when you have a phone in your hand, if you're watching me over your phone, there are a lot of complex circuitry are inside your mobile phone, right? So to name a few, you can see what are things I have kept on the screen. There will be a processor. Inside that, you will have a DSP, FPGA. Like there are so many digital ICs there. There will be high-speed serial links. There will be PLLs. Processor part will be there. Then you will see that there will be some memory part, right? There will be RAM, random access memories will be there. So many other related memory stuffs will be there. Then you will have something called as D2 and A to D converters, where I was talking about the analog circuits. Then we will have a separate division where we call it as power management, where you will generate different signals, different voltages in order to bias or in order to make work all these components or all these circuits inside. Then you will have other communication related things like Wi-Fi, Bluetooth, and the other IEEE standards protocols, where you can actually do all these communications efficiently. And you will have audio related amplifiers. You will have RF transceivers, which is one of the main core of your mobile phone, where the transceiver will help you to receive and transmit the signals. All right. So now, why I'm talking about this iPhone? See, if you remember, I was talking about engineering and science, then electrical electronics engineering in that VLSI. Then I have come to analog, and now I'm trying to relate that with your most modern device, what we use today. So what do you think? The mobile phone is coming to market not just like that. It is not the effort of a single person or a single company. A lot of different skilled people, different engineers are working under different domains in order to bring together a device which is actually making our life so easy today. All right. So if you look at that, there will be definitely component designers where they work on the component level. There will be circuit designers who take up these components and build circuits out of that to match all the requirements. Then there will be someone called as layout engineers. Layout engineers in the sense, if you have a circuit and if you want to translate that circuit into an integrated circuit or an IC, we will take the help of layout engineers who will perfectly lay out. So laying out is nothing but transferring a circuit onto a substrate or onto a chip. And we do have layout engineers. Then there will be process engineers who work in fabrication units, where they give all the process related rules, how you should actually draw a layout, how you should transfer the chip design onto a chip, and all the related details. Then you will have testing and validation engineers. So I haven't clearly demarcated between analog and digital. These are the general teams which will be working in order to design and develop a mobile phone. There will be testing and validation engineers. Then there will be PCB designers, where you need to, if you have multiple ICs and you want to bring those things together. It is not the printed circuit board what we generally see in a circuits lab, where we can actually directly hand place the components. In a much advanced versions of PCBs will be there. Then we'll have communication engineers who deals with the protocols and other related stuff. Then there will be memory designers who deals with the memory design, memory testing, and the related stuff. Then there will be EMI, EMC engineers who deals with this electromagnetic compatibility checks and other things. Then DSP engineers who deals with the processing part. Then system engineers will be there. Then network engineers, software engineers, and many people are there, right? So why I have listed all these things, it is this list is not complete. There are many other people who definitely really contribute to all these things, but I can clearly say that there is a role for each and everyone, especially the people who work on the component level, which is on the device level, and then the people who take up these components and design circuits in order to process all the signals which are coming in. All right. So this is my first part where I have just introduced the relevance of analog design. If you have any questions here, you can please post in the chat box. I'm happy to answer. Now, the next 20 minutes, we will quickly see about now one important device, because I was talking about the component and then the circuits. I would like to share, or I would like to talk a little bit more about one important device what we use today, that is MOSFET. And I don't know, I'm just assuming that all of you, I'm addressing from the responses. I know that most of you are first year students. That is why I'm addressing in that way. So you would have definitely heard about transistors, and we'll be talking about one transistor device, which is MOSFET. After that, we'll see. Yeah, we'll try to understand the difference between analog, digital, mixed signal, and RFICs. Then we will look at something called as technology node. Even though we will not use this term now as technology node separately, we'll try to understand what it is. Then we will look in little detail about what is about analog IC design process. And finally, we will I'll end this part with the question how to start. So if you are interested in doing something in analog, how to start with. All right. So if you have any questions, can I ask this question? Are you guys listening to me? If you're listening, can you just respond with an S in the chat box? Oh, thank you so much. Yes. All right. So I'm moving on. So if you have any questions, please at the end of the lecture also we can have a discussion. All right. So now first we will talk about MOSFET, right? So I hope all of you have heard about MOSFET and would have experienced MOSFET in some level. If not, it is an electronic device. Yes, so it is an electronic device. It is a transistor, basically a transistor, and MOSFET stands for metal oxide semiconductor field effect transistor. The picture what you're seeing on the screen is actually a cross section which is taken from Sedran Smith, a popular textbook of MOSFET on circuits. So yeah, those who know about this, maybe you will feel it as a cliche thing, but still I'll just give you a revision of the structure. So basically it will have two N plus regions. Why we mark it as N plus is because it is heavily doped region, and these N plus regions are grown on a P substrate, right? So on a P substrate, if you grow N plus regions, we call this MOSFET as N MOSFET. And one advantage or one specialty of this device is the gate. There are three. When you study about MOSFET for the first time, you might be introduced. You would have introduced MOSFET as a 3-terminal device, which is having a source terminal, gate terminal, and a drain terminal, right? But if you look at the actual structure, it is having 4 terminals. We call one more terminal as a body terminal. All right, and the gate of this device is actually isolated from the rest of the structure. You can see that gate is isolated, and there is an oxide layer which is present in between. All right. Now, so as far as a student, or as far as a circuit designer, or as far as an analog designer or an engineer is concerned, so to give you an idea, so devices, there are a set of people who do research or who work on devices and develop new devices. So they will be dealing much of the device physics part. So they'll be studying in detail about device physics, and they'll be actually modeling new devices, testing out new devices, right? So so I would say if you're looking or if you want to pursue a career in analog as an engineering student, I would say you have to definitely go back and read those device physics, which will give you more and more clarity. And I hope that all engineering degrees will have courses related to that. Now, with that knowledge, we will actually take up a device, right? So it is understood that, or it is we'll assume that yes, you know about the device operation. If you know about the device operation, the very important thing what I need to do or I need to analyze is the characteristics of the device, right? So whenever you have a device, an electronic engineer will look at the characteristics. The moment I say characteristics, I am interested to know the current voltage characteristics of the device. So why am I interested in the current voltage characteristics? Because I want to know if I vary voltage across the terminals of any device, how will the device respond? What current I will get out of the device, right? So in that line, if I look at the characteristics of MOSFET, so you can see that there are three terminals. I'm just, as of now, I'm just neglecting about body. Body terminal will be usually connected with the source for a reason. All right. So I'll tell you a little more about that. You can see the three terminals: source, drain, and gate. And you can also see that source and drain are placed on the P substrate. Now, the current what we are interested in this device is a current which is flowing from source to drain. And you can also see that it is not directly possible because there is no conducting channel between source and drain. So the device operation goes like this: whenever you apply a voltage to the gate, which will enhance or which will create a channel here between the source and drain, thereby a connection is established between source and drain, and that connection is established by the voltage at gate, and we call it as threshold voltage. And whenever you apply a voltage which is sufficiently enough to turn on the device by creating a channel, you will get a current flow if you apply a voltage between drain and source. Right. Now, that means the current which we are interested in this device is the current which is flowing from source to drain terminal. But you can also see that there are two PN junctions here, right? There is a P substrate and N plus layers are formed on this P substrate. Now, when you have two PN junctions, and at any point of time, if this PN junction turns on, there will be a current flow through the PN junction, right? So when there is a current flow through the PN junction, in fact, in the case of MOSFET, we are not interested in any other current than the current which can flow from source to drain. So when I operate MOSFET, what I'll try to do is I'll try to reverse bias the PN junctions here. You can see that between N plus and P, there is a PN junction. Again, between N plus and P, there is another PN junction. And in order to keep this PN junction off, shut off, we will always tie body terminal. For the body terminal of the NMOS device will be connected to the least potential in general. All right. All this again depends on the technology what you use. Similar is with PMOS device. The body terminal will be connected with the highest potential. The idea behind that is to shut off the PN junctions in the device. All right. I hope that is clear. Now you have a current which is flowing from source to drain. That is what you can see in the characteristics, right? So if I move on, these are two important cara what we are looking at of a MOSFET. When you vary gate voltage, how the current varies. When you vary drain voltage, how the current varies. So these two are very important, right? So from the characteristics, once you understand the cara, then we can see, once you understand the cara, you can actually, yeah, I'm just taking one cara out of that, ID VDS cara. And you will see that as you keep on increasing your drain voltage, you can see that current is increasing, and after some time current is becoming constant. And now this is possible when you apply a sufficient gate voltage, which should be slightly greater than the threshold voltage. Right. Now we can see two regions. Specifically, you can see two regions. One region we call it as triode region, or we call it as linear region, and another region we call it as saturation region. For the reason that in the triode region, you can see if you increase voltage, current is also increasing, right? So current is proportional to voltage. You can see to some extent it is proportional, and we call it as triode region. But after a specific voltage, we call this as overdrive voltage. After this specific voltage, the current is becoming constant. Our current is getting saturated, and this region we call it as saturation region, right? Now, by looking at the cara, we can say, yes, this is resistor, and this is actually acting as a current source. I hope you understand what a current source is. Current source is an element which will have a constant current irrespective of what we connect across it, right? The current, you can see that the cara of this MOSFET also behaves as a current source because after the specific point of VGS minus VT, whatever I do with respect to voltage, current is not changing. I should also add that this is the case of an ideal MOSFET, but in the case of a real MOSFET, you can definitely see some variation, and those variations are accounted or captured as something called as channel length modulation. All right. So once you understand so we should know about the device physics, then you should understand the characteristics. And once you understand characteristics, you know that, okay, if I want to get a resistive behavior, how I should bias the device. If I want to operate it as a current source, how I should bias the device. So basically biasing is fixing the voltages in order to operate a specific device in a specific region. All right. Are you guys with me? Are you following what I'm telling? Can I get some response in the chat? All right. Thank you. Thank you so much. Yeah. So in between, I can see some of you are not able to follow. Yes, if you have any questions, you may ask at the end. All right, fine. Yeah, so just to brief, device, and once you get a device, you understand the characteristics. Yes, Kapil, I understand. Sometimes it need more explanation. Yes, I do understand that. Yeah, but if you have questions, definitely at the end of this segment, you can ask, you can definitely post your questions, or even in between, I can answer to those questions. All right. Yeah. So so those who did not get, I can say that, see, if I want to work with some electronic gadget, if I want to design something, I need help of devices. So you should understand about device behavior, device operation, and then device SCADA. For a circuit engineer or a circuit designer, characteristics is very important. So once you understand the characteristics of a device, you can actually say that, or you will have a control that, okay, now if I bias this device with this much voltage, this will act as a resistor. Now, if I bias this device with this much voltage, it will act as a current source, right? Now, MOSFET behaving as a resistor and MOSFET behaving as a current source will have definitely implications. That is what we are going to see now. All right. Now, if you have a MOSFET which can work as a resistor, which can be operated as a resistor, when I say, the moment I say resistance, so what I need is in digital ICs. So the use of MOSFET in resistors is basically coming in digital ICs. So as we were discussing about digital, you told that digital is about digital is something what computer understand, or in a very primitive way, if you say digital is actually all about zeros and ones, right? So if I want to convey a logic, a digital logic, what I need is whether the logic is giving you a 1 or giving a 0. That means I need switches. Basically, I need switches. So for a switch, so what are the two modes of operation of a switch? Either the switch will be on or the switch will be off. Now, if your switch is on, what I need is it should not provide any resistance. The resistance should be actually 0. Right? If the switch is on, whatever I need to pass, I should get it. Now the switch is off, whatever I pass, it should not come out, right? The resistance offered by the switch should be actually infinity, right? Now, MOSFET in triode region can act as a switch, a wonderful switch. So by providing sufficient voltage at the gate, that is to operate in linear region, it can actually act as an on switch with minimum resistance. So switches, ideal switches will behave with a 0 resistance when it is on and infinite resistance when it is off. But practically, when you implement that, it is not the case, right? So when the switch is on, it will have some minimum resistance. The switch is off, it will have a huge resistance, infinite resistance, so that it will function as a switch. Now, why are we talking about MOSFET switch? Very important in digital IC, because if I want to implement switches, that too, if I want to implement a lot of logics, right? So we cannot do that with the physical resistors, what you practically see in your lab, because those resistors are actually, they are bulky. They dissipate a lot of heat, and bringing those into an integrated circuit and making it as the what to say, miniaturization is not possible. So as I was talking about Industry 3.0, semiconductor industry flourished because of ICs, integrated circuits, where the possibility of bringing many components together onto a substrate, and that has flourished like anything, where you can actually bring in millions of transistors together on a platform, on a single platform, right? And today, whatever we see in our mobile, in our laptop, the new most modern processors, there are huge millions of transistors we are bringing together, right? Now, when I say millions of transistors are coming together, each transistor size is very, very small, right? Now, miniaturization is possible. We can actually bring in a huge logic, and we can actually get a lot of, yes. All right. Yeah, so this is what all about this MOSFET is. So we're using digitalization. Now, coming to the current source, we will actually use in analog ICs. So whenever you talk about an analog circuit, we use MOSFET as a current source, right? So just I'm differentiating between digital ICs and analog IC. When I say digital IC, we intend to use MOSFET as a switch, but in analog IC, we will have, so in digital ICs, we'll only have switches, MOSFET switches, but in the case of analog ICs, you will have MOSFETs and we'll have resistors. But when you bring in capacitors into this, we call it as mixed signal IC, because the moment you bring in capacitor, the whole intention is actually to store your analog signal and then you convert it. That is basically happening in an analog to digital converter, the mixed signal IC. And The moment you have one more component, the very basic component inductor, we call it as a radio frequency integrated circuit. And because inductors are part of RFICs, radio frequency ICs. All right. Now, to just brief about MOSFET, it is 1928. It was patented by Lilienfeld, but because of the lack of manufacturing fabrication process, it was not fabricated. The first MOSFET has come out in 1960, which is again manufactured by Bell Labs, but it happened only after the BJT. We look at the structure. We have looked at the structure. One important thing is we mentioned as the length of the MOSFET, which is a distance between the source and drain, and this is often called as feature size or the process node or the technology node, alternatively used. And there are slightly differences between when we use all these three different terms, right? So why I want to bring in here this is I just want to tell you that nowadays, I don't know how many of you are aware that these days there are companies who work on 3 nanometers or even lesser than that transistor sizes. So it all depends on the technology node. So initially when the integrated circuit started, the size of the MOSFET was in the form of microns, where we call it as micron process. It could be more than 10 micron also. And when it is less than 1 micron, so what is this 1 micron? 1 micrometer is actually the distance or the length of the MOSFET. Length is basically the distance between the source and drain. Now, when it comes less than 1 micron, we call it a sub-micron process. So as the length is scaling down, or as the size of the MOSFETs are scale down, what happens? As the MOSFET undergoes scaling, the MOSFET size becomes smaller and smaller, and we can integrate many number of transistors into an integrated circuit. All right. Now, when the size of the MOSFET comes less than 100 nano, we call it as nanometer process, right? And today you can see that some of the process nodes are listed here. I have listed up to 5 nanometer. And if you specifically look at digital functions, it has been implemented in lower nanometers technologies as well. But in the case of analog functions, at least less than 22 nanometer or less than 32 nanometer, we will see that it is not a planar MOSFET no longer. It is not a planar MOSFET. Rather, we'll have fins coming up, and we call it as FinFETs. And it again, it is in relation with the Moore's law. As you know that the number of transistors in an IC doubles every 18 to 24 months is what Moore initially predicted. And now it is something more than Moore is what we are seeing. Again, bringing back to the chipset of iPhone 7. So we, through this iPhone 7 chipset diagram, we actually looked at the different people who are working on this. But now I want to explain the process behind an analog IC design and a digital IC design, right? So as you can see that there are digital functions and analog functions in a mobile phone chipset or whatever electronic gadget you take. If it is an analog design, you will start with a specification. A specification is something what we want to achieve at the end. So when you come up with a circuit, say for example, you are talking about amplifier circuit. What I need to have is, all right, if you have this, if you have I need an amplifier which can actually increase the gain of my voice signal up to 50 dB, 50 decibels, right? That is one of the specification. So once the specification is ready, we will look after the system design, where you will have a larger picture. It is not only amplifier, it is not only an oscillator or a memory. The system design talks about everything. Now, from the system design, we will decide that, okay, which all things need actual circuits, which all things can be implemented in digital, which all things can be should be implemented using actual circuits. So then we'll talk about the circuit design. And once the design is ready, we start with simulations, because we were talking about MOSFETs of nanometer technology, where you cannot go to a lab and handpick the component, connect it on a breadboard or a PCB, and you cannot test it, right? So because the size is very, very small, you cannot handpick it. So you need to actually, the process, or we call it as a fabrication unit, where these transistors are getting fabricated or manufactured. And before sending, or before that process happens in a fabrication unit, because it is an expensive process, we need to design the circuit and we need to test it. Test it in the sense, we basically first we do simulations. Now, how do you do simulations? With the help of softwares, right? That is why whenever you see VLSI, you will also see an attached lab, which will be a computer lab mostly, not a hardware lab where you can go and handpick the components. The reason is the nanometer technology MOSFETs, the behavior of those nanotechnology MOSFETs are very well modeled, and those models are available in the form of design kits. We call it as PDK, process design kits. Those kits will be available in the software. There are different softwares. We'll be discussing about that now. Now, using those softwares, we can design and we can actually try different simulations. Once the simulations are performing well, once the circuit simulations are performing well, we can go for system simulations. Once those simulations are perfect, we can actually go ahead with the layout design, where you will transfer the actual circuit into an IC by laying out the design. And once that is done, we can go ahead with the top level interconnect, then verification, and finally fabrication. Even though I have mentioned it as a very easy 5 to 6 steps, the actual process is not like that. It is very tedious and it is very time consuming. All right, for analog design. Now, one advantage for digital design is, this is all about analog IC design, where you have to design a circuit, where handpick the components, you have to choose the aspect ratio or the size of every transistor, then you have to continue with your designs. When it comes to digital design process, it is a little different, where you will get little more help from the tool, where you can auto generate your circuit, because there in analog IC design and digital IC design process, there are in 2 ways. You can actually start your design entry in 2 ways. One is, in analog IC design, we'll start with a schematic entry, but in a digital design, you will actually start with your HDL entry, where you will actually use a hardware description language to write a code, a piece of code, and then using that code, we'll be synthesizing. There is a process called synthesis, where your circuits will be automatically generated, right? Then we are not much worried about the sizing of the transistors, but in the case of analog IC design, we'll be looking after the size of each and every transistor. But in the case of analog digital IC design, the reason is, since in the digital ICs, the transistors are acting as switches, we don't need to do much with the sizing part. Rather, we can actually auto generate the circuit if you have a logic. Once that is done, you can also auto generate the layout. And once that is done, you can, after auto routing, after verification, it will go to fabrication, right? I have shown this as 2 different things. Again, it depends on, are you manufacturing a single IC or you have a complete SOC kind of stuff. All right. I hope you guys are with me. If you guys are with me, or if you're listening to me, can you just put an S in the chat box? All right. Thank you so much. Now I'll talk little more detail about analog IC design process. So I have another 20 minutes of time. I'll be winding up my presentation. So the very first thing is actually to brainstorm the ideas. You have to, it is not like, in certain times you'll be working on the existing designs, but in most of the cases, at least now as the technology is progressing, you'll be actually brainstorming a lot of ideas. Then you have to come up with the system level design. Once that design is ready, you have to go with the design component or the circuit level design. Once that is ready, you can actually start with the simulations. You can see one random simulation that is basically to verify the functionality of the design. And once that is done, we can actually translate the complete design, the circuit design, into the layout form, which is called as design physical translation. And once layout is ready, we can actually fabricate the IC. There are different steps in between. And once it is fabricated, it will be packaged, right? Because I'm talking about a single IC at this time. So it can be packaged. Once it is packaged, you can test and debug the IC. So that will be again done in a lab by connecting this on a PCB with the related circuitry, and we'll be testing and debugging it. Once that is done, you will be prototyping the specific thing. And then you will characterize and you see that whatever you have seen in simulation, whether those things are actually coming up again, or what is the deviation between the simulations and the actual IC. And then it may either go for an evaluation board, or it can go to the commercial products as well, where we will be getting your final product, right? This is what it is behind a typical analog IC design process. All right. Now, so as students, if you're listening to me as first year students, I would say, if you're asking the question how to start with, I would say you should start with devices. As I was telling, you should understand about devices, the device physics, study about devices, because that will give you a lot insight how you can actually work later on. Now, once you know about devices, you can actually understand about the terminal character. That is an obvious thing, right? So when you study about devices, definitely you will talk about the device characteristics or the terminal characteristics. Once you know about terminal characteristics, you can actually start learning about circuits using the specific device. If the MOSFET is a device, you can actually learn about circuits using MOSFET. So this thing is the fundamental thing, and that has to be done. What to say? No, we will not get any help from a software, or we will not need not take any help from the software, because this is something which we have to do and we have to be thorough about, right? And as engineering students, you will definitely have courses to learn about these things. Now, once this is done, as I was mentioning, you can start designing circuits, and for that we will be taking the help of softwares, where you will actually enter your design in the form of a schematic. You will do functional check and you will do layout. And for this, you will actually get the aid of a computer. This is very important because I have seen, at least I have advised to my own students that, see, once the software is there, it is not like you have to go jump. Siddhant Gupta, I can respond to your question because I didn't get your question exactly. How to use old phones as devices. I'll get back to a question after this. All right. So now what I'm talking about is, if you have a software, say for example, there are various simulation softwares available. It is not like you have to just start with the simulation, but you have to come through the step, the process, know the device, understand the CARA, and then you learn about circuits. Once that is there, you can actually start with the schematic entry, then the functional verification and layout, and there are a lot many softwares which will help you to do that. Right. Now, are there any questions here? Are there any questions so far? Siddhant, your question is how to use old phones as devices. I didn't understand the context of that. Devices refers as, yes, yes. Yes, of course, Gayatri, Ashok. Yeah, it is also a part of that. Quantum computing is actually an emerging field. I would say even it needs a lot of computer science knowledge as well. Yeah, you can actually think about it is an emerged field out of that. I can say that. Yeah. So the time what I have left is around 20 minutes. Actually, I was telling I planned for another segment as a third segment here, where I wanted to actually talk a little more about the models of analog design, the gain calculation, the overview of amplifiers, the specifications, and some design example and simulation. So what I will do is, sorry, because that that will take a little more time. If you have questions on that, I'll definitely come back to this after the last segment, because this is something what I planned as a typical lecture where it needs another at least a half an hour of time. All right. So what I'll do is I'll actually go to the last segment. Right. So now what I want to present is, to start with, in order to, if you want to start to work as an analog designer, or if you want to start with analog design, which all courses you need to study, what are the software tools available, what are the fabrication facilities what we have, and what are the present challenges what we can still work on analog, and the further opportunities what we have. All right. So the courses are, I would say, you have to be thorough with the device. I haven't included devices because it is an obvious thing. Devices should be device physics, and the devices nano other things should be definitely there. Then you have to learn about circuits. Then you have to circuits in the sense you have to learn about discrete circuits and integrated circuits as well. Then, as I was talking about analog IC, digital IC, mixed signal IC, you have different courses actually to undergo and learn analog, mixed signal, RF related component. And then now, whenever you learn these courses, there should be an associated theory laboratory. Definitely, you will have that a laboratory where you can actually go and using like a hardware lab as well as a software lab using EDA tools. Right? These are very, very important when you want to pursue something in this area. Now, if you look at the different software tools available, EDA tools available. One of the most popular tool is Cadence, provided by the company called Cadence Design Systems, which is called as Virtuoso. In that, you will actually do the designs. Then Metagraphics provides something called a Spanner. Then Synopsys is having Custom Designer, and Silvaco, another tool, another software which provides something called as Gateway. So all these software companies provides a set of EDA tools, electronic design automation tools. I have specifically mentioned about the circuit design entry tools only here. Right. Now, if you do not have any of these, we can actually start with something called as open source softwares. And one of the free open source tool to start with is actually LT Spice, which is provided by Analog Devices. If you can just Google LT Spice, download, you can directly go to the download page, and where you can download the software and you can work using the software, right? But please keep in mind, before download, you can download before working on that, see that you have actually a knowledge about the device properly. Now, if you have a design, now with the help of the softwares, you can design it. Now, if you have a design, how to actually, how to make it, or how to finally fabricate it, or how to get a chip in your hand, right? So as I was mentioning, we will have PDK, process design kits, which will be provided by the foundry. So have to study about the CMOS process and the PDK is available. That will be done with the help of the characteristics itself. Now, if that is done, next we can actually go ahead with the circuit schematics simulation, right? So we can study the state-of-the-art architectures, specifications, study selection of architecture, then manual designs, then you can actually come up with simulations. Once simulation is done, you can actually go for the physical design of the layout, where I was mentioning in the even the previous slides as well, where you will have layout design rule, and there are a lot many other rule checks to do that. Once physical design is done, you can actually go for something called as post layout simulation. A simulation is done twice. One is before layout and one is after layout. Because after layout, you will actually get a more real characteristics or the real response of any circuit or any system. And once this post layout simulation is done, you will actually go for something called as Monte Carlo simulation and adding IO library, because for any IC, there will be input output pads. So those there are a lot of process involved there. Those will be done in that step. And finally, once all these things are done, the final step is actually to tape out. So when I say tape out, putting seal ring, putting silicon number, the dummy fill, all these things, and sending these files into a fabrication unit, right? So these are the various steps involved. Again, even though you see it as a 6 steps, I would say if you, as an engineering student, as an undergraduate student, if you can come up this step 4 is actually a good thing. Now, with the support of the fabrication facilities, what we have in India, definitely you can tape out and you can see the designs coming up, right? To mention some of the foundries, the fabrication facilities, as I was mentioning about the process design kits, there are different companies provide this. TSMC is one company, UMC is another company, Global Foundries, Samsung, there are a lot many companies. And one central government organization, which is under ISRO, we call it the Semiconductor Laboratory, which is in Chandigarh. They also have this, we do have the fab, they do have a fab here in India, in Chandigarh, and they have the facility to fabricate till 180 nanometer technology chip designs. All right. So having an MOU with SCL, getting the PDK and you can start working on that. That is another thing which is possible. Now, coming to the challenges, what we have today in analog design is, one thing is transistor imperfections, because the size of the transistors are coming down, and we are actually modeling transistors in a software and we are trying out with that. So there are at least certain things we will not be able to capture the behavior of the transistors perfectly. So transistor imperfections will definitely create some issues. Then the supply voltages are actually coming down. When I say declining, previously, if the supply voltage was 5 volt, we are actually coming to a low voltages, right? Like 1.8, 1, even very small voltages we are working with. So that is another challenge, because see, for example, you have an existing design which works for a 5 volt. Now, scaling your power supply, now the requirement is for 1 volt, means it is not, it is not mandatory that the same design should work for your low supply voltage. That is another task. So we need to actually work for that. Sometimes we need to actually come up with new circuits itself altogether. Another thing is power consumption, because we know that we all look for, previously we were talking about low power, but now we talk about minimum power. So how can I operate a device or a circuit or a gadget with minimum power? So power consumption is an important area or important challenge now. Then the circuit complexity, because there are a lot many circuits which were working fine with the many number of components when you have a larger power supply. But now when you scale down the device, when you scale down the power supply, bringing those complex designs in the new skeleton is also a complex task these days. Then about process voltage and temperature variations, because even the PVT variations are something which is very important when you talk about IC design. And finally, there are many layout related effects coming up. All right, so these are design challenges what we have today, where different people are working on these different things. Along with this, people do work on various other things as well. So I just want to showcase some of the opportunities what you have to do research in this area. Yeah, one is modeling of new devices, because right, the requirement will keep on increase, and people are trying out new devices. It is not only the planar MOSFET what we are talking about. We do have FinFETs, and then we do have different combinations of semiconductors coming up with trying out with for the different performance metrics, performance parameters. So modeling of new devices is a very important and very upcoming research field, where lot devices are already available, and still lot devices are not even tested in all the analog related areas as well. Yeah, so in the similar line, you can also talk about novel circuit architectures and techniques, because when a new device comes up, it is not mandatory that all the previous existing biasing or the related circuitry will work with this new device as well. So we may need to come up with some modifications in the existing design. These two are something which related to the analog or the device physics part. Then we do have rest of the other things, which is the part of VLSI, where we can work for design for testability, then algorithms for design automation. You can talk optimization of standard cells, developing standard cells. Sorry, I might be using some new terms. If you have any questions on that, definitely I can take those questions at the end. So I'm trying to wind up as the time is. I have only another 5 minutes, five or 6 minutes of time. Now, if some of you are very interested, very keen in doing something on analog design, I could say that the current research focus. So these are some of the current research focus I can say. One is on Nyquist ray data converters. You would have heard about successive approximation ADC, or you would have heard about delta sigma ADC. People do work on data converters because as the technologies and the power supply voltages scale down, accuracy of data converters is something which is very important these days. Now, if you ask me the question, why do accuracy plays a role here? Because if I want to convert an analog signal into digital, you have to, if I have a signal of this much, and when I convert an analog signal to digital, you have to replicate the signal with the most accuracy. Otherwise, you will be conveying the wrong information to the other set. So that is very important. That is on the data converters part, but there are something called as low power RF transceivers, basically for all the communication devices, where you have to develop low power. I would like to reframe it as the minimum power RF transceivers, and people do work on filters as well. These are some of the moving on. You can also see that there are post-Moore ICs and systems where you hear about photonics, you hear about mixed signal photonics, where instead of looking for an electron flow, people already there are researches happened, and there are things coming up in photonics. Then you can also see something related to neuromorphic computing and edge AI. So all these things, I could say that if you are a student, a first year student, all starts with the device physics and your circuits, and you can actually progress and actually come up to this level or even more. So there are a lot of ample opportunities ahead, and the presentation what I had given here is actually in a very nutshell form. Different things I have placed together. Sorry that I could not actually cover the details of the analog design in a normal lecture way, and I hope that would have been definitely covered, will be covering in your regular schedule. But if you're interested, definitely we can have discussion. I'm in touch with Dr. Navjit Baga. So if some of you are interested to work on this, you can definitely, I'm associated with Dr. Navjit, we are planning to collaborate for some of the analog design. So if you're interested, definitely you can contact sir, and we can definitely work on that. So thank you so much for a patient listening on this Saturday evening, and thank you so much for giving me this opportunity to talk to you and interact with you guys. So I extend my sincere gratitude and thanks to IIITM Jabalpur and Dr. Navjit Baga and the department, and Ankit for IEEE Nanotech Council for giving me this opportunity to interact with you. Thank you so much.
Thank you so much, sir, for such an explanatory presentation. And you also explain us from the scratch to the industry aspect. And I also like to tell if you to the participant, if you are a B.Tech student, so we have a courses Sir said to you that we have an analog IC design, physics of semiconductor devices in your pre-final year and final year curriculum, and we also have a lab associated with that. So we are teaching you cadence virtuoso software for the simulation purpose. So it was a great experience for all of us that you shared with your time, sir. And with this, I open the room. If you have any question from the participants, so you can ask directly from.
Thank you so much, sir. Thank you so much. I hope Ankit had already shared a feedback form there. That is actually the feedback about the session. Please feel free to mention things over there. If you have further questions, even you can write it in the feedback forum, which is already given. Which is already Ankit, will you be able to post it again in the chat?
Yes, sir. I will do that.
Yeah, thank you. Are there any other questions? Because some of the questions what I have seen in between, I answered then and there itself. Are there any other questions?
I request the participant, if you have any question, you can type on the chat, or you can directly unmute yourself and ask.
Yeah, it will be better if you can type in the chat so that it will not disturb others. Thank you for the comments which has already come in the chat box.
I have already posted the feedback form, so please, I request to all of you, please post your feedback in the given link. Okay.
Right. Thank you.
So now, now with this, now we came to the end of this event. So before that, I request Mr. Rajiv Jaiswal sir to please give a vote of thanks for our guest.
Thank you, Ankit sir. On behalf of our IEEE NTC chapter and Optica student chapter team, I extend a really hearty vote of thanks to our chief guest, Dr. Nithin M, who spared time from his busy.
Rajiv sir, can you hear me?
Yeah. Am I audible, sir, now?
Yes.
Sir. So sorry for that, applies. I'm really thankful to Dr. Nithin M sir, who spared his time from his busy schedule to grace the occasion. Today we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our future events. Now I request all the participants to switch on the camera for group photograph.
Yes, I request all the participants to please switch on your camera so that we can have a group photo. Okay. Okay, thank you once again to all of you. We have Navjeet sir in the audience. So Navjeet sir, would you like to say something?
Yeah, thank you so much for this complete NTC Council and Dr. Nithin. He gave his time for this valuable complete talk. I'm really sorry. Actually, I joined late because I was in another meeting. We had a discussion with Dr. Nithin as well. So I'm really thankful. And from on behalf of complete this NTC chapter, Optica and PDPM Jabalpur, IIIT Jabalpur, we thank Dr. Nithin. And we believe that in the later stage of time, we will have some collaboration in terms of talks, in terms of work as well. And I'm very sure that B.Tech students, M.Tech students, and Ph.D. students gained a lot of knowledge in terms of analog domain. Generally, if you see in our college, in other colleges also, people having some fear on the analog because generally you see what you are doing, devices domain, digital domain. So analog domain is also a very nice and important domain. Generally, we don't go in that, but I believe that after this talk, definitely we can think of at least research in part of analog domain itself. So once again, thank you, Dr. Nithin.
Thank you, sir.
Thank you. Thank you for giving this opportunity.
Thank you, complete NTC team for this.
Thank you, sir. So with this, we are come to at the end of this event. So as a token of appreciation, I would like to our guest to give a kindly accept this digital copy of the appreciation certificate. We will soon send this the hard copy of the certificate, sir.
Sure. Thank you so much.
So at last, I'd like to thank all the participants to join this session and make it more informative to all of us. So thank you so much to all of you. Now we are okay to end this meeting. Thank you, sir.
Thank you once again, Ankit. Thank you. Bye.